Hi everyone, I am Kishore KR. I would like to introduce the basic concepts of histogram specification. First of all, let me start with the basics. What is histogram? In simple words, histogram is a graphical representation of the tonal values of your image. In other words, it shows the amount of tones of particular brightness found in the image ranging from black to white. That is from 0% brightness to 100% brightness. Here, the figure 1 represents the histogram of the image A. The histogram is obtained by a simple code in the MATLAB, that is IM_hist of A. In digital image representation, the given image is divided into many pixels. Corresponding to each pixel, there will be an intensity level associated with it. Practically, we assign 256 levels of intensity to an image. That is, we represent the image intensity levels ranging from 0 to 255, where 0 represents the black and 255 represent the white. Now let's see what a histogram of an image actually contains. In this figure, it is just a model of how a histogram looks like. Here, x-axis is the intensities varying from 0 to 255 and y-axis is the number of pixels. For example, a dark picture will have more number of pixels occupying lower intensity values. Here, the peak values lies in the lower extreme region, whereas a white image has a peak values of extreme right ends. And in between the 0 and 255 is the gradient of intensities from black to white transition. Histogram specification. Histogram specification is the transformation of an image so that its histogram matches a specified histogram. Here, the input image is to be transferred to the histogram specified by the reference image. Clearly, the output image got the characteristics or histogram of the reference image. To make the concept more clearer, let's take an RGB image. Now it's quite evident that the input image got transformed as per the histogram specified by the reference image. This is the physical significance of histogram specification. Objective. Here we want to convert the image so that it has a particular histogram that can be arbitrarily specified. Such a mapping function can be found in 3 steps. Equalize the histogram of the input image, equalize the specified histogram, and relate the two equalized histograms. Histogram specification in a nutshell. Now let's look at the overall procedure behind the histogram specification. The first step of histogram specification is the histogram equalization. The cumulative distribution function of the histogram equalized images are computed at the second stage. Then a proper mapping function is to be formulated to get the modified image. Histogram equalization. It is a technique for adjusting the image intensities to enhance the contrast. Let F be an image represented by a matrix capital M of R rows and C columns. The integer pixel intensities ranging from 0 to L minus 1, where L is the possible intensity values, often 256, then normalized histogram of F with a bin for each possible intensity Pn equal to number of pixels with intensity n divided by the total number of pixels, where n varies from 0, 1, 2 up to L minus 1. Now let's see the physical significance of histogram equalization. Here the left hand side represents the raw image. Now after applying the histogram equalization, the image is transformed to the image at the right side. This can be easily achieved by a MATLAB code histeq of A. Now let's see the math behind this transformation. Raw image has histogram as given in the left side. After applying the histogram equalization, it gets modified to the one at the right. Clearly, the intensity values are equalized to number of pixels in the right hand side. All the intensities will occur at equal probabilities. Hence, CDF is a linear curve with a smooth transition from 0 to 1. Now, let's explore the math behind the histogram specification. We first equalize the histogram Px of the input image x. Y is equal to f of x equal to integral 0 to x Px of u du. We then equalize the desired histogram Pz of the output image. Y dash is equal to g of z equal to integral 0 to x Pz of u du. The inverse of the above transform is Z equal to G inverse of Y dash. As the two intermediate images Y and Y dash both have the same equalized histogram, they are actually the same image, that is Y equal to Y dash. Overall transform from the given image to the desired image can be found to be Z equal to G inverse of Y dash equal to G inverse of Y equal to G inverse of f of x. However, as the image gray levels are discrete, the continuous mapping obtained above can only be approximated. The discrete histograms hy of I and hy dash of I are not necessarily identical. We therefore need to relate each gray level in X with hx of I not equal to 0 to a gray level in Z with hz of I not equal to 0 so that the mapping from Y to Y dash can be established. Steps of the algorithm. Step 1. Find histogram of input image hx and find its cumulative capital Hx, the histogram equalization mapping function capital Hx of j equal to summation I equal to 0 to j small hx of I. Step 2. Specify the desired histogram Hz and find its cumulative distribution capital Hz. The histogram equalization mapping function is given by capital Hz of j equal to summation I equal to 0 to j small hz of I. Step 3. Relate the mapping to build a lookup table for the overall mapping. Specifically, for each input level I, find an output level j so that capital Hz of j best matches capital Hx of I. That is, modulus of capital Hx of I minus capital Hz of j equal to minimum of k modulus of capital Hx of I minus capital Hz of k. And then we set up a lookup entry, lookup of I equal to j. To make the math more clear, let me introduce an example. The histogram of the given image and the histogram of the desired are shown below. Here, two histograms are given. First one, it is the original histogram, and second one, it is the specified histogram. Original histogram is nothing but the histogram of the input image. Now, the specified histogram is the histogram of the reference image. In histogram specification, our objective is to change the histogram of the original image with the histogram specified by the reference image. Step 1. Equalize Px to get mapping y equal to f of x. Here the first column represents the levels, capital Xi, where I ranges from 0 to 7. I is nothing but the intensity levels. Here for convenience we take 8 intensity levels. That is 0 belongs to black and 7 belongs to white, and in between we have the transition values from black to white. Here, the second column represents the number of pixels corresponding to each of the intensity levels. Now, the third column is the equalization. Equalization values are computed by dividing each of the nj values with the total number of pixels. That is, dividing the number of pixels corresponding to each intensity value by the total number of pixels in that image. This constitutes the PDF of the image. Now we need to calculate the cumulative distribution function, which is nothing but the cumulative addition of the present probability value with all the preceding probabilities. It is quite obvious that the CDF corresponding to the last intensity value, that is the last row, corresponds to 1. Now we have prepared the values for the CDF corresponding to the input image. Step 2. Equalize PZ to get mapping y dash equal to g of z. The same procedure is repeated for the step 2. Hence, after step 1 and 2, we get CDF of both the input image and the histogram specified image. Step 3. Obtain overall mapping x to y, y to y dash, and y dash to z. This is the most critical step in the histogram specification. Here xi denotes the intensity levels varying from 0 to 7. Second column yj equal to capital Hx is the cumulative distribution function of the input image. Third column yj dash equal to capital Hz is the cumulative distribution function of the histogram specified image, and the fourth column capital Zj equal to j is also the intensity level of output image. Now from step 2 and 3 we have the values for capital Xi, capital Yj and capital Y dash j. Now in step 3 we will calculate capital Zj. Now we need to calculate the values of capital Zj equal to j. For that, consider the first row. Here I equal to 0 and capital Yj equal to 0.19. Corresponding to the value 0.19 in capital Hx, we need to find a value in capital Hz which is very much closer to 0.19. In capital HZ, we can see that corresponding to 0.19, there is 0.15, which is the most closest value to 0.19. And the intensity value corresponding to 0.15 is 3. And that's why we put J is equal to 3. So in lookup table, we write for corresponding to I equal to 0, we have J equal to 3. Now let's see the second row. Here I equal to 1 and capital HX value is 0.44. Now we have to find a value which is closer to 0.44 in capital HZ. Now, corresponding to 0.44 in capital HX, we have to find a value in capital HZ. We have 0.44 in between 0.65 and 0.35. The difference between 0.44 and 0.65 is 0.21, whereas the difference between 0.44 and 0.35 is 0.09. We have to take modulus while taking this difference. Corresponding to each value in capital HX, we have to find the values in capital HZ, which is more closely located to capital HX. So for 0.44, we take the value 0.35 instead of 0.65 because it is more closer to 0.44. Corresponding to 0.35 in capital HZ, we have the intensity value of I equal to 4. So we map I equal to 1 to J equal to 4. So this is the second entry in our lookup table. Now let's take I equal to 2. Corresponding HX value is 0.65. Now we need to search HZ values which is having more closer to 0.65, and we can see that 0.65 is readily available, that is with no error. 0.65 can be mapped to 0.65 itself. So corresponding to 0.65, the intensity level is 5. So this means that I equal to 2 corresponds to J equal to 5. Now let's take I equal to 3. Corresponding capital HX value is 0.81. Now searching for the closest value in HZ, we have 0.85 in HZ. So corresponding intensity is 6. So we can say that for I equal to 3, the mapping in J is equal to 6. So I equal to 3 is J equal to 6. So that value is also defined. Now for I equal to 4, we have Hx as 0.89. So correspondingly in Hz, we can select intensity value of 6. So we can say that for I equal to 4, we have J equal to 6. Now for I equal to 5, we have Hx as 0.95, and for I equal to 6 as 0.98 and I equal to 7 as 1. For all these three values which are very much closer to 1, we can map to capital Hz equal to 1. So these three values will find an entry to an intensity level of 7. So I equal to 5 have J equal to 7 and I equal to 6 also have J equal to 7, and similarly the 7 is also mapped to 7. Now the lookup table is ready. Now after applying the transformations, the input image transforms itself to an output which is having the histogram specified by the reference image. Now let's summarize the mathematical procedure like this. we are given two images. First one is the input image whose histogram is to be changed, and second one is the reference image whose histogram is taken as a reference. Now, after applying the histogram equalization and computing the cumulative distribution function, we are arriving at a criteria or a lookup table which transforms this particular histogram of this reference image to this input image. And finally, we are getting an output where the input image is having a histogram of the reference image. Now let's put hands on the MATLAB for having a better feel of the histogram specification. These are the commonly used codes which are very much important for histogram specification. A equal to im read of path. This command is used to read the input image. B equal to im resize a comma scale. Scale the image A by a scaling factor of scale times. X equal to double of x represents x in double. B equal to zeros of n returns n by n matrix of zeros. B equal to cum sum A returns cumulative sum along the array. Im show of I displays grayscale image of I. Im hist of I displays histogram of image I. Now let's have a quick review of code. We all are familiar with CLC, close all, clear all commands. Now the first section of the histogram specification code is for reading the images and doing proper scaling. Here A is the input image and B is the reference image. Now, after proper scaling of both the images, we have to go for histogram equalization as a first step, and after that calculation of cumulative distribution function. Here we represent the intensity level of image at 256 levels. Here two for loops are required for calculation of the cumulative distribution function and one for loop for calculating the histogram equalization. Now the same code is repeated for the input image as well as the reference image. That is, first step is histogram equalization and after that calculation of CDF. Now the third level is the crucial step, as we have already seen, is the preparation of lookup table. For preparing the lookup table, we need 3 for loops. Instead of 8 level, here we are using 256 level. Hence, the value from capital HX to capital HZ is to be compared with all the 256 levels. And when the value is closest, we will break the loop and map the corresponding I in capital HX with J in capital HZ. Now we got the lookup table mapping from I to J, and the output image is drawn with the specified histogram. Now we are coming to the last part of the code where all the images are plotted. That is the input image, histogram specified image and the output image which is modified according to the histogram specified. Demonstration using MATLAB. Now this is the input image which I have chosen. This is nothing but the central library of NIT. Now, I'd like to take some reference images that will transform this particular input image according to the histogram specified by that reference images. Let's see what is happening. In the left hand side, I have shown the reference images which I have taken, and in the right hand side, I have shown the resultant transformation that has taken place for my input image. Clearly, the resultant image is modified according to the reference images. Here also, we can see that the reference image histogram is transferred to the resultant image. So, the input image is getting changed or modified according to the histogram that is specified by the reference image. Histogram specification is having a lot of applications. Just one among the many applications is the retinal image enhancement. Here the input image is dark, and in the reference image we have chosen in such a way that all the nerves and the retina is clearly visible. So the input image get modified according to the histogram specified by the reference image, and we can see that the resultant image is having a higher clarity or higher visibility than the input image. The references. You may go through these websites and textbooks for having a much more clear idea about histogram specification. Thank you.